You are welcome to SK Pass International College. If you have not subscribed to the channel yet, please kindly subscribe to the channel. Watch the video, comment, and bring your input. I would like you to share to your colleagues in different schools. Alright, we are still on the topic hybridization. Just like to remind you, chemistry is chemistry. So please try your best as we do more examples. Try your best to also do more examples to understand the concept in a simpler way. Today, let's quickly look at formation of Ethyne. Okay, so in our previous video, we were able to form Ethyne. Okay, and we gave a general formula for all alkenes. But with this Ethyne, we are going to give the general formula CnH2n-2. Okay, so when you're having C2, okay, H2 times 2 will give us 4 minus 2. So you are going to get C2H what? 2 times 2 is 4, 4 minus 2 is 4. Sorry, it's 2. So the chemical molecular formula for this Ethyne is C2H2. So this Ethyne, one thing before we start with the whole work, one thing we need to understand about this Ethyne is Ethyne, the type of hybridization that exists between the carbon-carbon atom. Look at this. This is a triple bond. So it means Ethyne is supposed to have one sigma bond with 2 pi bonds. Ethyne compared to the other one we did in our previous video, which is Ethyne, this will be quite more reactive than Ethyne. So having said this, it means anytime we are dealing with a triple bond, it means the type of hybridization that will occur is going to be an sp hybridization. In sp hybridization, it's formed as missing one s with one p. So let's look at how it is formed. So let's quickly work on the central atom. This time around is C2H2, but still our central atom happens to be carbon, and we have done that several times. So let's write the configuration: 1s2, 2s2, then 2p2. This is called the ground state. This is called the ground state electronic configuration. Now, when you are done with that, you quickly write the excited state. We only use the valence electrons. So in this case, if you are to use the valence electron, we are going to focus on this 2s, and then so this is having 2 electrons, this has 2. But just like I explained in my previous video, we don't use 2 electrons in chemical bond. It's only 1, then it pairs with 1, then they share, and then they become they form a bond. So this one will have to promote this electron from this lower energy to a higher energy. So it has promoted this here. So this will eventually vanish. So this electronic configuration, this is px1, py1, and then pz1. This is called an excited state electronic configuration. Now your ability to do this, you can now mix these orbitals. But bear in mind that this molecule, that is Ethyne, the hybridization existing in between the molecule is an sp hybridization. So what it implies is that we are only going to mix one of the s with one p. So let's have a view of the diagram. This is my carbon, the first one, just like we did in the previous presentation. There are 2 of the carbons, so you can see the atomicity of this carbon is 2. So we are going to work on 1 and repeat the same to the other carbon. So with this one, when I mix one s and with one p, I form 2 hybrid orbitals. And these hybrid orbitals prefer to stay far away from each other. They prefer to stay far away due to repulsion. So this will be formed here like this. 1 is here. 1 will not be formed here. They need to repel. There should be a repulsion. So this will also stay far away. So So this is how they are going to stay far away from each other. So these two hybrid orbitals have been formed. Now with this first carbon, what is happening here? The same thing is happening in this carbon. It is also forming two hybrid orbitals. So with that, we can say this, so we can say this is also forming a hybrid orbital here. Let me do it well. So this is my carbon. Then there's another one, another hybrid orbital. Now, if you check this clearly, you realize that this is forming something linear, like a straight line. And this should give you a clue that the type of hybridization this is undergoing is an sp hybridization. And we have said severally that anytime a molecule undergoes an sp hybridization, the shape of that molecule is linear in shape. So you can see this is creating a linear shape. So that is the shape we are getting. Now, having said this, you can check from this level that the bond angle, the angle on a straight line, angles on a straight line will have to sum up to 180. So the bond angle of this is 180. You can see that from the linear shape. Now, however, there are two of the orbitals. They have electrons ready to undergo chemical bonding, but they were not used because of the type of hybridization. So this is one of them, and this is another one. So quickly, they need to have their position. They need to appear because they are having electrons. They are capable of undergoing chemical bonding. Just that they were not used. So we use only the S and the P. So these two are called on hybrid orbitals. They need to appear on the molecule to show that they have electrons. Now, this is the shape of the px, just like we said. So px looks like this. This is the shape of the py, and then the pz is here. So having said that, let's pick this. This is py. So automatically, py from this place is going to behave like this. It's like this. So that's the shape. So this is py. Now the same thing is happening here. So this will also behave like this. So it's like something like slanting a bit. Okay. The same thing is happening here. So this is what we call py. This is py. This is unhybridized. So let me shade that portion. This is py. Shade that portion so that it will be obvious. Now this is not the only unhybridized orbital. We also have pz, which is also unhybridized. But this is how the pz looks like. So pz would prefer to be like this. Okay, so this is pz. Okay, it is straight, the plane. So this is pz. Another one also occurs here. It is having the same streets. So this is pz. Now I want to give pz a zigzag shape like this. Okay. So that we can differentiate the two. So if you look at this carefully, if I want to join, this is py and this is pz. This is py and pz. So from here, we use literal lines. Pi bonds are formed, so pi bonds. We use literal lines to indicate. So let me join this p. This is the first one. Py, we join py. So this one, we use hidden lines to join this. That's form a pi bond. Py will still join py. So this one has joined py. Now, if you look at the other side, pz will also join pz. When it comes to this side, pz will join pz with hidden line or broken lines. So if you look at this bond form here is a sigma bond. Now this is a pi bond, this is another pi bond. So just like I said, if you view the diagram in the upwards direction, it has formed one sigma bond with two pi bonds. or someone will view the diagram in the lower direction, downwards. If you view it downwards, it still have one sigma bond with 2 pi bonds. And this is exactly what we are talking about. This is having 2 pi bonds with 1 sigma bond, and this is what has been formed. So this is how sigma bonds and pi bonds are formed. And from this ethyne, we have demonstrated that this ethyne has 1 sigma bond with 2 pi bonds. And this is the exact thing we are talking about. It's having only one hydrogen. Now these are the hydrogens. There are only 2 here. And hydrogen on the periodic table is on the S block. It's spherical in shape. So we are going to indicate one here. Then we indicate the other one here. So this is my hydrogen. This is my hydrogen. This hydrogen will donate 1 electron. This carbon will donate 1. They share to form a covalent bond. This will donate 1 electron. This will donate. They share to form a bond. So the covalent bond formed here, the covalent bond formed here is what we are seeing here. And this is the pi 1 sigma bond and 2 pi bond. 1 sigma bond with 2 pi bonds. This is what we are seeing. So this is the diagram of what? Ethyne. This is the diagram of ethyne. Now with this, I want to talk about the last thing, and then we draw the curtains on this chapter. Now the last thing we talk about is to know the differences between diamond okay, so this is just a structure, a very simplified structure of diamond. And then we want to also look at a simplified structure of graphite. In graphite will take more time. Graphite. Okay, so I want to give a simplified diagram. Now this structure you are seeing, we have another one downwards like this, the same structure, downwards like this. So this is exactly what we are seeing. Now these two structures, they link up with each other with hidden lines. Look at this. This end will link up with this end like this. Okay, this will link up with this like this. Okay, so they are linking up. The molecules in there are linking up like this. Okay. Okay. So this is what we call graphite, and this is diamond. Now from these two diagrams, you can talk about the carbon. Look at the carbon. These are carbons located here. The carbons located here. Now the carbons here, 1, 2, 3, 4. You can see 1, 2, 3, 4 like this. It's tetrahedral in shape. So when you pick diamond, the carbon, okay, on every diamond, the type of hybridization for this carbon is an sp3 hybridization in diamonds. But when it comes to graphite, the type of hybridization here, look at this. This is 1, 2, 3. It looks like a triangle. Look at this. It looks like a triangle. So we call this a trigonal, and it is having the carbon there is having an sp2 hybridization. So this is a clear difference. On the carbon existing in the diamond has an sp3 hybridization. This carbon existing in this graphite has sp2 hybridization. Now in terms of their molecule, this diamond is a very hard substance. Okay, very harder. compared to even metals. But this is soft. That's why we use this in making pencils. And this is used for making what? Jewels. So you can also look for some differences between this diamond and graphite. Post your answer in the comment section and let's discuss it. Thank you for watching this video. Subscribe to my channel, like the video, and see you in my next presentation. Bye bye for now.